28th March 1945, 21:30 hours. A lone Avro Lancaster from 223 Squadron crosses the Dutch coast at 8,000 feet, its 4 Merlin engines throttled back to cruising power. Inside the fuselage, where bomb racks once hung, a different cargo occupies the space. 6 tons of electronic equipment fill the compartment from nose to tail: oscilloscopes, transmitters, frequency analyzers, and a bewildering array of dials calibrated in megacycles. Flight Lieutenant James Thornton adjusts the headphones clamped over his leather flying helmet, listening to the frequencies. At precisely 21:45 hours over the town of Arnhem, he flicks a series of switches on the main transmitter panel. Instantaneously, across a front stretching from Nijmegen to Wesel, German ground controllers attempting to vector night fighters lose contact with their aircraft. The carefully orchestrated defensive system, dependent upon precise radio communications between radar stations, control rooms, and cockpits, dissolves into static. For the next 27 minutes, the electromagnetic spectrum over the Rhine crossing points belongs entirely to the Royal Air Force. This was not an isolated incident. It represented the culmination of a technological arms race that had begun nearly 5 years earlier, when a small group of scientists at the Telecommunications Research Establishment realized that the same physics governing radar could be weaponized in reverse. The problem facing Bomber Command in 1940 had been brutally simple. German night fighters, guided by an increasingly sophisticated network of ground-based radar stations designated Würzburg and Freya, were destroying British bombers at an unsustainable rate. During the winter of 1943-44, loss rates on certain operations reached 7.2% per sortie. The mathematics were brutal. A bomber crew's tour of duty consisted of 30 operations. 7.2% losses per sortie translated to a survival probability of precisely 13.8% for a complete tour. Bomber Command was hemorrhaging trained aircrew faster than the training schools could replace them. The strategic bombing campaign, upon which considerable Allied planning depended, faced potential collapse not from enemy action, but from simple arithmetic. The German defensive system operated with mechanical precision. Freya early warning radars, operating on frequencies between 120 and 150 megacycles, detected incoming bomber streams at ranges approaching 100 miles. This information passed to divisional headquarters, which scrambled night fighters and directed them towards the general area of the raid. As the bombers penetrated deeper into Reich airspace, the shorter range but more accurate Würzburg sets, working at 560 megacycles, acquired individual targets and guided fighters to within visual range. The coordination depended entirely upon radio-telephone communications between ground controllers and fighter pilots, transmitted on very high-frequency channels between 38 and 42 megacycles. British intelligence officers, analyzing interrogation reports from downed Luftwaffe aircrew and signals intelligence intercepts, reconstructed the system's architecture with impressive precision. They identified the vulnerable point, the radio links themselves. Every communication system possessed a finite signal-to-noise ratio. Introduce sufficient noise, and the system failed. The challenge seemed insurmountable. German transmitters operated at kilowatt power levels. Creating interference strong enough to overwhelm these signals would require airborne transmitters of equivalent or greater power, a technical impossibility given the weight and electrical constraints of 1943 aircraft. The solution emerged from an unlikely source. Dr. Robert Cockburn, a 32-year-old physicist working in the countermeasures section at TRE, proposed a fundamentally different approach. Rather than attempting to match German transmitter power, British jamming equipment would exploit a quirk of radio propagation. A receiver could only process signals within a narrow frequency band, typically between 50 and 200 kilocycles wide. German fighters and ground stations tuned their receivers to specific frequencies to minimize interference from adjacent channels. Cockburn's insight was deceptively simple. A jammer need not overpower the desired signal across all frequencies simultaneously. It needed only to sweep through the relevant frequency range rapidly enough that the target frequency remained jammed for a sufficient percentage of time. The mathematics supported the concept. A transmitter cycling through 4 megacycles of spectrum at a rate of 1,000 sweeps per second would dwell on any individual frequency for 1 millisecond per second. Radio-telephone communications, however, required continuous signal presence. Breaking the signal for even 50% of the transmission time rendered speech unintelligible. At sweep rates above 500 cycles per second, the human ear perceived the jamming as continuous noise rather than periodic interruption. The German operator, attempting to issue course corrections to a night fighter, would hear nothing but a rasp of static across his headphones. Cockburn's team designed and built the first prototype in 11 weeks. The equipment, designated Type AN/APR-1, but known universally by its operational codename Airborne Cigar, consisted of 3 main components: a motor-driven rotary spark gap that generated the sweeping interference signal, a high-power transmitter rated at 750 watts, and an array of 4 tuned antennae protruding from the bomber's fuselage. The entire assembly weighed 386 pounds and required a dedicated operator. Installation occupied the space normally reserved for the mid-upper gun turret, and the weight penalty reduced the aircraft's bomb load by approximately 1,200 pounds. The first operational sortie occurred on the 7th of October, 1943. 8 Lancasters from 101 Squadron, each fitted with Airborne Cigar and carrying a specially trained wireless operator designated the Special Operator, accompanied the main bomber stream attacking Stuttgart. German controllers reported severe interference on all RT channels. Post-operation intelligence analysis, comparing German fighter sortie rates and claim rates against previous raids of similar size and route, suggested a reduction in interception effectiveness of approximately 30%. Bomber losses on that night totaled 3.1%, against a predicted loss rate for that target and defensive sector of 4.8%. The Germans responded with predictable efficiency. Within 6 weeks, Luftwaffe signals officers began deploying backup frequencies and experimenting with frequency-hopping protocols. Night fighter pilots received instructions to maintain radio silence except during critical phases of interception. Ground controllers increased transmission power and narrowed receiver bandwidth to improve signal-to-noise discrimination. Each countermeasure prompted British countermeasures. By January 1944, Airborne Cigar equipment had evolved through 3 major variants, each incorporating additional frequency coverage and improved jamming waveforms. The crucial development occurred in February 1944, when 100 Group formed at RAF Bylaugh Hall under Air Commodore Edward Addison. Unlike conventional bomber groups tasked with attacking specific targets, 100 Group existed solely to support the main bomber force through electronic warfare and airborne jamming. Addison assembled a remarkable collection of resources: 8 squadrons of modified heavy bombers carrying jamming equipment, 3 squadrons of night fighters equipped to hunt German night fighters, and a headquarters intelligence section staffed by signals analysts, physicists, and German-speaking intercept operators. The group's operational doctrine evolved rapidly. Initial missions employed small numbers of jamming aircraft dispersed throughout the bomber stream, each covering a portion of the electromagnetic spectrum. Intelligence analysis revealed a more effective approach. Concentrating jamming aircraft along specific routes created electromagnetic corridors through which the main force could penetrate with reduced attrition. On the night of 24 March 1944, 23 aircraft from 100 Group formed a jamming screen extending from the Dutch coast to the Ruhr industrial region. Main force bombers, routing through this protected corridor, experienced loss rates 40% below the 3-month average for comparable operations. Equipment proliferated. Airborne Cigar targeted voice communications. A second system, designated Tinsel, used microphones installed in the bomber's engine nacelles to pick up engine noise and rebroadcast it on German fighter frequencies, creating a background roar that masked controller instructions. A third system, Jostle, employed considerably higher power to jam ground-to-air transmissions over broader frequency ranges. By June 1944, a typical 100-group Lancaster carried between 600 and 900 pounds of jamming equipment, operated by up to 3 specialist operators in addition to the normal 7-man bomber crew. The manufacturing effort proved substantial. Pi Radio Limited, operating from facilities in Cambridge, delivered the first production batch of 90 Airborne Cigar installations in December 1943. Production accelerated sharply through 1944. By May of that year, Pi's assembly lines were completing 42 installations per week, each unit requiring 127 vacuum tubes, 86 precision capacitors, and hand-wound transformers specified to tolerances of plus or minus 2%. Total production ultimately reached 823 complete systems at a unit cost of £2,847, exclusive of installation labor and airframe modifications. The operational deployment pattern evolved into a sophisticated choreography. Jamming aircraft took off 30 to 40 minutes before the main force, flying predetermined tracks designed to activate German early warning radars and provoke defensive responses. Once German ground controllers began transmitting vectors to night fighters, the special operators initiated jamming across all detected frequencies. The main bomber stream, following 10 to 15 minutes behind, encountered a defensive system already degraded by electronic interference. German controllers, unable to vector fighters effectively, resorted to broadcasting general warnings and predicted bomber tracks, hoping pilots would achieve chance interceptions. Enemy response took multiple forms. German signals intelligence identified the jamming aircraft by their distinctive transmissions and developed procedures for targeting them specifically. Luftwaffe fighters claimed 23 confirmed kills of jamming aircraft between October 1943 and April 1945. The jamming equipment itself radiated powerful electromagnetic signals that could be detected and homed upon. Some German night fighters carried receivers tuned specifically to Airborne Cigar transmission frequencies. Special operators learned to recognize the telltale signs of a fighter homing on their emissions and developed evasion protocols. Brief transmissions followed by course changes, random frequency hopping, and coordinated jamming with other aircraft to create multiple false targets. Statistical analysis of raid outcomes provided compelling evidence of effectiveness. Bomber Command's Operational Research Section maintained meticulous records correlating jamming effort, raid parameters, and loss rates. Between October 1943 and May 1945, operations supported by 100 group jamming aircraft experienced average loss rates of 2.77%, compared to 4.23% for operations without electronic support. Applied across the 162,000 bomber sorties flown during this period, the difference represented approximately 2,366 aircraft and 16,500 aircrew who survived operations they statistically should not have. The campaign's sophistication increased dramatically in the final months of the war. Intelligence gathered from captured equipment and decoded signals revealed that German controllers were experimenting with ultra-high frequency communications above 100 megacycles to evade British jamming. The response came remarkably quickly. Modified jamming equipment covering frequencies up to 150 megacycles entered service in January 1945. The Germans shifted again, this time to microwave frequencies above 3,000 megacycles. British engineers designed equipment to counter these systems, but the war ended before deployment became necessary. International developments followed parallel trajectories. American forces, initially skeptical of electronic warfare's utility, established their own jamming units after observing British operations. The 36th Bombardment Squadron, redesignated the 803rd Bombardment Squadron in June 1944, operated modified B-24 Liberators carrying American-designed jamming equipment designated AN/APT-3. The system employed different technical approaches but achieved similar results. Joint operations over Germany in 1945 occasionally saw British and American jamming aircraft working in coordinated patterns with careful frequency deconfliction to avoid mutual interference. The Germans themselves never developed equivalent offensive jamming capabilities. Their strategic situation precluded it. Electronic warfare required carrying heavy equipment over enemy territory, accepting reduced bomb loads or fighter performance as a consequence. German forces, fighting defensively for most of the war, optimized their aircraft for interception and direct combat rather than electronic support. When they did attempt jamming operations during isolated raids against British cities in 1944, the efforts proved ineffective. British ground-controlled interception systems, designed with German jamming attempts in mind, incorporated frequency diversity and jam-resistant coding that rendered German transmitters largely irrelevant. Assessment of the campaign's strategic impact requires nuanced analysis. The absolute numbers appear modest in context. Electronic jamming did not stop the German night fighter force. Luftwaffe pilots continued claiming bomber kills throughout the war, including successes against jamming-protected formations. Loss rates declined, but never approached zero. The campaign's significance lay not in total suppression, but in incremental advantage. Reducing loss rates from 4.2% to 2.8% sounds unremarkable until one calculates the cumulative effect over tens of thousands of sorties. The difference between these percentages represented the viability of the strategic bombing campaign itself. The psychological impact may have exceeded the material effect. German night fighter pilots, interviewed after the war, consistently reported frustration with unreliable communications and the sense that British bombers operated with impunity despite defensive efforts. Ground controllers described the jamming as a relentless presence that transformed their work from precision vector control to desperate attempts at rough positioning. The defensive system never collapsed completely, but it operated under constant degradation, its effectiveness eroded by invisible electromagnetic interference. The technical legacy proved substantial and enduring. Every principle developed by 100 Group between 1943 and 1945 remains relevant to modern electronic warfare. The concept of sweep jamming, using frequency-agile transmitters to deny communications across broad spectrums, forms the foundation of contemporary radar jamming systems. The tactic of concentrating jamming assets to create protected corridors through hostile airspace remains standard doctrine. The integration of signals intelligence, jamming operations, and strike missions into coordinated campaigns established the template for modern suppression of enemy air defenses. Equipment survived in remarkably small numbers. Airborne Cigar installations, pulled from scrapped bombers after the war, were classified for decades due to their technical sophistication. The Imperial War Museum at Duxford holds one complete system, restored to operating condition in 1998 by former TRE engineers who had worked on the original development. The installation occupies a preserved Lancaster fuselage, complete with the operator's station, oscilloscopes, and the characteristic antenna array protruding from the fuselage sides. Visitors can see the rotary spark gap mechanism, its beryllium copper contacts still bearing the erosion marks from millions of high-voltage discharges. Archival research continues revealing operational details previously unknown. Documents declassified in 2003 disclosed the extent of signals intelligence integration with jamming operations. Special operators received not only frequency information, but often transcriptions of German controller instructions, allowing them to anticipate defensive responses and time jamming bursts for maximum effect. The intelligence loop operated with impressive speed. German frequency changes could be detected, analyzed, and countered within 12 hours, sometimes faster. This responsiveness proved as important as the jamming equipment itself. Personal accounts from special operators paint vivid pictures of the work's nature. Squadron leader Malcolm Leng, who flew 38 jamming sorties with 101 Squadron, described the peculiar isolation of the role. While the rest of the crew fought flak and fighters, navigated through darkness, and concentrated on reaching the target, the special operator inhabited a different war entirely. His battle occurred in the electromagnetic spectrum, invisible and abstract. Success manifested not in explosions or fires, but in silence, in the absence of German transmissions, in the spaces between communications that indicated jamming effectiveness. Failure was equally abstract: a sudden increase in clear transmissions, a coordinated fighter response, a sense that the defenses had adapted. The operational hazards extended beyond direct combat. Jamming equipment generated substantial electrical noise that interfered with the bomber's own navigation and communication systems. Special operators learned to coordinate jamming bursts with the navigator's radio fixes and the wireless operator's status reports, creating brief windows of electromagnetic silence during which the crew's own equipment could function. The high-power transmitters produced intense electromagnetic fields that occasionally caused compass deviations or induced currents in the aircraft's control cables. Multiple incidents of unexplained control difficulties were eventually traced to jamming equipment operating at maximum power in specific frequency ranges. The financial cost proved modest relative to other aspects of the bombing campaign. Total expenditure on jamming equipment development, production, and operation between 1942 and 1945 reached approximately £12.4 million. By comparison, the aircraft lost to enemy action during the same period represented a replacement cost exceeding £450 million. If electronic warfare reduced losses by even 3%, the equipment paid for itself 36 times over. These calculations assume monetary costs only, ignoring the incalculable value of air crew lives and the strategic consequences of sustained bombing operations. Post-war analysis by German air defense commanders provided perhaps the most telling assessment. General Joseph Kammhuber, architect of the Reich's night fighter system, acknowledged in interrogations that British jamming had forced continuous adaptation and resource expenditure. Each British innovation required German counter-innovation: new frequencies, new protocols, new equipment. The defensive system, Kammhuber noted, expended considerable effort simply maintaining effectiveness against electronic attack, effort that could not simultaneously address improvements in bomber tactics, navigation, or target selection. The jamming campaign, he concluded, had not defeated the night fighter force, but had distracted it, forcing defensive rather than offensive optimization. The human dimension merits recognition. The 2,847 air crew who served as special operators flew under conditions of exceptional stress. They performed complex technical tasks whilst airborne over hostile territory, often under fire, in cramped spaces filled with high-voltage equipment that occasionally arced spectacularly in the darkness. Unlike other crew positions, their contribution to the mission remained invisible to their colleagues. A successful sortie for a special operator meant that nothing happened, that German fighters failed to intercept, that controllers gave up attempting to vector aircraft through the electromagnetic chaos. Recognition came slowly and incompletely. The Distinguished Flying Cross citation for Flight Lieutenant Thornton, whose jamming operation opened this account, makes no mention of electronic warfare, describing instead his contribution to navigation accuracy and crew coordination. The intellectual achievement deserves particular emphasis. Between 1940 and 1945, British scientists and engineers created an entirely new form of warfare from theoretical principles. They identified vulnerabilities in enemy systems, designed equipment to exploit those vulnerabilities, developed tactics to employ the equipment effectively, and established organizations to coordinate these activities with conventional operations. They accomplished this whilst the enemy adapted continuously, forcing constant innovation under operational pressure. The campaign represented applied physics and engineering at their most demanding, with lives depending directly on technical performance. Nobody at the Telecommunications Research Establishment in 1942 could have predicted where the work would lead. The initial investigations into German radar systems, intended merely to understand enemy capabilities, evolved into offensive electronic warfare, which became integral to strategic bombing operations, which influenced the war's outcome in ways both subtle and profound. The progression occurred through hundreds of incremental developments, each seemingly small, collectively transformative. Dr. Cockburn's insight about sweep jamming, dismissed by some colleagues as too simple to work effectively, ultimately contributed to saving thousands of lives and maintaining Allied bombing pressure when German defenses threatened to make daylight and night operations equally suicidal. The story concludes where it began, in the electromagnetic spectrum over occupied Europe. On the night of 28 March 1945, Flight Lieutenant Thornton's Lancaster completed its jamming mission and turned for home. German ground controllers, their frequencies saturated with interference, abandoned attempts at vectoring night fighters and transmitted instead generalized warnings of bomber presence. The main force crossed the Rhine, largely unmolested. Thornton's crew landed at RAF Faulsham at 0247 hours, having flown for 6 hours and consumed 1,847 gallons of aviation fuel to carry electronic equipment that weighed less than a single 1,000-pound bomb. The weight-to-effect ratio seemed absurd until one considered the alternative. Attempting the same mission without jamming support would likely have cost 12 to 15 bombers, 80 to 100 aircrew, and accomplished nothing more. Technology triumphed not through brute force but through understanding. The British electronic warfare campaign succeeded because it operated on a deeper level than the German defences it opposed. Where German systems sought to detect and destroy individual bombers, British jamming attacked the information architecture that made detection and destruction possible. The distinction proved decisive. Physical systems could be defended, repaired, replaced. Information systems, once disrupted, could be restored only by changing the entire structure of communications and control. Such changes required time, resources, and institutional adaptation that the Reich, fighting on multiple fronts with diminishing resources, could not provide. The lesson remains relevant 8 decades later. Electronic warfare persists as an essential element of modern military operations, its principles unchanged despite technological advancement. The frequencies have shifted from medium wave to microwave to millimeter wave. The equipment has shrunk from bomber-filling installations to pod-mounted systems. The underlying logic endures: deny the enemy the ability to coordinate, communicate, and control, and even superior forces become ineffective. The mathematics remain as brutal and unforgiving as they were when Bomber Command calculated survival probabilities in 1943. The difference between success and failure, between survival and destruction, measured not in tons of bombs, but in wavelengths, frequencies, and the physics of electromagnetic propagation, proves time and again that the most effective weapons need not be the most powerful. They need only be the most precise.